Right. So can you see my slide that is remote position control system? Is it visible?
Yes, ma'am.
Okay. So now we will turn up. Okay. So what we are going to do today is an application of some of the control system components that we've already studied, which are used to perform a specific objective. Now over here, the system that we are about to study is a remote position control system. So as the name implies, it is a position control system, obviously, and it may be operated from a remote location. So the name. Now I'll come to more of that at the end of this when we have already, studied a bit about it. Now you can see the diagram over here. Diagram means the photograph on the top left, which actually shows a dish antenna. You can see that. Now, basically, the objective over here would be to track a target which is in the sky. I hope you can see my cursor. Now, let us say that the target is somewhere over there. So, this dish has to be oriented such that its axis is uh, along the direction, meaning along the direction of the line connecting the target to the dish. So that, say, for example, if the target is placed over here, this would be the line connecting the target to the dish. So the dish axis has to be rotated accordingly such that it is pointing exactly in the direction of the target. So this animation over here, it's downloaded from the net and not a very good one, but you can see that basically the dish would be moving, not like, like it is visible over here, only two places you can see it pointing. Actually, it's going to be pointing at a particular direction, any direction, and accordingly, depending on whether the target is moving or not, it would have to change its angular orientation in, you can say, synchronously with the target. So if the target is moving, the orientation of this antenna would also have to be changing such that it is then pointing towards the new position of the target. So here now what we have at the bottom, this diagram is a schematic diagram, a schematic diagram showing a remote position control system. So I mean, I'll just give you an overview of what is there, what uh, components are used over there, some of which you would be able to recognize from what we've studied so far. And then we will go to the notations. We'll describe the notations then, meaning that you can see a lot of, symbols are used over there and notations thereof, what they signify with the proper units. And then what we will do is we will derive the transfer function for this overall system, meaning the model of the overall remote position control system is going to be derived. And then we will see how this system is able to achieve its objective. Achieve its objective means that it should be pointing towards the direction for which it has been designed, meaning that if a reference position is given, the output shaft should actually be pointing in that direction, right? So to start with, first of all, over here in this diagram, you can see this unit. I hope you can see the cursor again. So this unit is the potentiometric error detector. You can see that, right? So potentiometric error detector, you can see the two pointers here and there. And these elements are, of course, though they are shown as straight line elements, meaning shown as straight line strips, actually they are circular elements because we are going to deal with angular position over here as far as this particular system is concerned. So, a more precise, or you can say, an exact representation, if you wanted, you could have actually put a circular elements over here and there. But nevertheless, since theta r and the angular rotation thereof is already written, you can understand that that is what is being meant. So it's, it's a common practice in many books. You would find that such, even for angular parts, basically, such elements are shown. But since theta r, as I told you, angular position has been indicated, you can understand that, we mean physically, construction wise, these are going to be these are going to be circular in nature, right? So you can see the voltage source, you can see the pointers. Now over here in this potentiometric error detector, there are two angles that are indicated. One is the reference, right? So this is the angular position of the reference shaft. In this one, you can see the other pointer is coupled to, via this dotted line, it is coupled to the load shaft. So I'll come to the load a bit, later. So overall, the output of this potentiometric error detector will be proportional to the difference between the reference signal, that is theta r, and the feedback that is coming. It's going to be proportional. The output voltage of this potentiometric error detector will be proportional to the difference in between these two signals, right? Now, next, what you see is over here an amplifier unit which has a gain. It's indicated over there. We'll come to the symbols later on. And then after the amplifier, you see that the amplifier output is feeding a servo motor. So DC servo motor is what you see over here, and you can also recognize the mode which is being used over here, meaning whether it's field controlled or armature controlled. You can understand from this. Can anybody tell me which mode it is connected in from what you can see over here? This particular unit. You can see that the supply is being connected across the armature, right? So it is an armature controlled DC servo motor, while the field current is kept constant. We had studied that in the last class, right? So basically, this is an armature controlled DC servo motor, right? Then the armature shaft is coupled via a gearing arrangement. You can see that over here. It's a hand drawn, diagram, but more or less understandable, right? So you can see over here via this gearing arrangement, this shaft is coupled to the load shaft. So the load is over here given by this GL and FL. These two units over here indicate the load, right? So this portion is the load unit. Load shaft is coupled to the motor shaft via this gearing arrangement. Also, what we see over here is that there is a mechanical coupling shown by the dotted line of the load shaft with the input side meaning the potentiometric error detector, which I already mentioned earlier. So that is in short the components that you see over here, right? So basically the potentiometric error detector, the amplifier, DC servo motor, gear unit, and the load unit are what we see over there, and of course the feedback is there, the mechanical feedback, right? The mechanical coupling will be such that this is going to be a difference, meaning theta r minus theta c will generate the output of the potentiometric error detector. So now coming to the next slide, which gives us the notations and the units thereof for the different quantities. So first we have theta r is the angular displacement of the reference input shaft in radians. So this is the reference shaft. Theta r is its angular position, right? And the unit is in radians. It could have been in degrees, in which case all the other units would have also, would also be appropriately changed. So here it is taken in radians for this analysis. Next, we define another notation, that is theta c. You can see that over here. It's the angular displacement of the output shaft in radians. Now, as you can see, this theta c is actually coupled to the output shaft, right? So basically, theta c is the angular displacement of the output shaft in radians. Next, we have theta L. So theta L is the angular displacement of the load shaft in radians. So theta L comes over here. And for this particular diagram that you see over here, theta C will be equal to theta L because it is directly mechanically coupled to the load shaft. The output shaft and the load shaft are mechanically coupled directly. Now, one thing that can be mentioned over here is that in general, there could have also been a gear train over here between this, this shaft over here and the load shaft. So, if there would have been a gear train with a non-unity gear ratio, then we would have also had to consider that ratio between the theta c and theta l. However, over here the coupling is shown straight and direct, I mean. So theta L and theta C are the same thing for this particular system that you are seeing. Theta L is the angular displacement of the load shaft in radians again. Next is theta M, right? So theta M is the angular displacement of the motor shaft in radians. So you can see theta M over here. This is the motor shaft. You can see that. Theta M is the angular displacement of the motor shaft. Obviously now this theta M, rather this shaft is coupled via this gear train to theta L. So there will be a ratio of conversion depending on the gear train ratio, right? So it will be a simple, I mean, uh, number by which you would have to multiply so that you can convert from theta L to theta M or vice versa. Next, we define Ke, which is the sensitivity of the potentiometric error detector, also known as the gain of the potentiometric error detector. So now over here, as far as this potentiometric error detector is concerned, you find that the output of this potentiometric error detector is in, what is the unit? It is in volts, right? And what is the unit of the input, that is the thetas? It is radians. So Ke unit will be volts per radian. It's going to convert from radians on the input side to volts on the output side. So unit is volts per radian. I'm specifically mentioning these units because, I mean, you would have to keep these in mind when you are doing the analysis. Specifically, if you are dealing with numerical problems, you would have to say, for example, if your theta r is specified in, say, as 20 degrees or 35 degrees or something like that, then you would have to appropriately change everything from degree to radian and so on. So, I mean, it's obvious, of course, but anyway. Now we come to Ka. So Ka is the amplifier gain, this one, right? So Ka, and basically the output of the amplifier is in volts, the input of the amplifier is also in volts. So it is, I mean, unitless, or rather, I mean, here we've mentioned it as volt per volt because it is converting from a volt to a volt. So for clarity, it is written as volt per volt. Next, we have VA, which is the applied armature voltage in volts. So this is the output of the amplifier unit, which is connected across the armature, right? So that is VA in volts, armature voltage in volts. Next, we have RA. Now, there is a slight mismatch in the notation over here. Basically, I mean, as far as the diagram is concerned, we've used small RA. I keep on forgetting to change this notation over here in the writing, which is easier for me. But anyway, so here RA, I mean, capital RA and small RA denote the same thing. That's one thing you have to keep in mind as far as this diagram is concerned. So R, small r suffix small a, is what we have over here as the armature winding resistance in ohms, right? Next, we have IA, which is this one, the current in the armature winding in amperes, right? Next, we have LA, which is the armature winding inductance. Now, you would recollect that we had actually discussed that the armature winding inductance is negligible and often considered zero. So over here, we've mentioned that it is negligible because when we actually derive the model, we will be making this simplifying assumption in order to derive the model. If the armature winding inductance is provided, naturally we know how to deal with it because we had actually, if you recollect, in the armature control DC servo motor, when we had derived the model, we had first derived the entire model and then we had said, okay, if LA is equal to 0 or negligible, that is, this is the simplification that you have. So if, I mean, you have to consider, you can, over here, we are going to neglect it because it is negligible. Next, you have EB, which is the back EMF in volts. It's not shown on the diagram, but you can understand that it will be the back EMF produced in the armature in volts. And KP is the back EMF constant, which is the unit is in volts per radian per second. So it is volt second per radian. If you recollect, it was converting from your from your angle or rather sorry angular velocity to the appropriate voltage, so the unit will be accordingly taken, right? So volt second per radian. Next we have JL. So JL is the moment of inertia of the load in kg meter square. Next we have FL, which is the viscous friction coefficient of the load, this one in Newton meter second per radian, right? So, and we also have Km, K suffix capital M, which is known as a motor torque constant in Newton meter per volt. And we have Jm, this one, which is the moment of inertia of the motor, right? So over here, basically in this system, I've not completed the list, one or two more, but in this, you see that the motor is there and it is also coupled to a load. So basically the moment of inertia of the load and the motor have to be separately considered initially, and then you, have to consider both those effects if you are dealing with the model, so that the overall moment of equivalent moment of inertia is taken. Similarly, with the viscous friction coefficient, load and the motor have to be considered together. So Fm is the viscous friction coefficient of the motor. It is negligible, but anyway, so the notation is Fm. So those actually are the notations which have been used in the diagram over here, and IF of course is the field current which is constant, and the gear train has a ratio which is written over here. Small n is to 1 is the gear ratio. That about completes the listing for the notations. So next, just coming to something before we go into the actual derivation of the model. So over here now you find this is a ship, you can recognize that, and basically in ships what is done is that such radars, or rather yes, radars or dish antennas are placed on the deck of the ship, say over here or somewhere on the deck, and they need to be pointing towards the, say, enemy aircraft or something, right? So there will be a person who is sitting within the control room and then dialing in a command. Dialing in means that they will be setting that, okay, my theta r reference command is so, such and such degrees, it is 10 degrees. So they will be using something like this. This is of course a sort of primitive version that's shown over here just for your understanding. So maybe a steering wheel like this or etc. will be used. Of course, nowadays such arrangements are replaced by, you can understand, electronic components, but nevertheless, whatever, just for your understanding. So basically this person will be sitting somewhere at a remote location. Why I'm saying remote location is that he will be sitting inside this control room and giving the command to the radar dish so that it is pointing towards a specific target, right? So that is where or why the position control system is actually a remote position control system. Alternatively, what could happen is that this dish, it's not placed on the ship, but maybe it is placed on the top of a hill or something, and at the foot of the hill you have the control room. So the person who is controlling or putting in the command signal will be sitting somewhere else at a remote location, putting in the command such that the dish is pointing towards the target. So basically, as far as application is concerned, remote position control system will be used in such applications. Now coming to the model itself, we will be deriving the model by taking the units separately, meaning each of the units that we have over here, the model of each will be written down first, and then the overall model of this remote position control system will be derived thereof, right? So first of all, coming to the potentiometric error detector. So the output, that is E or epsilon S. So epsilon, the equations are directly written in the Laplace domain. You find that you could have written it in the as differential equations and taken the Laplace transform. That's, of course, understood. I hope you understand that. So here now, epsilon S is the output of the potentiometric error detector, and it's proportional to the difference between theta and theta c. So epsilon S is equal to some constant Ke into theta r minus theta cs, where Ke is known as the sensitivity. And as we stated, Ke will have the unit of volt per per angle. Or if the angle is in radian, it's radians, right? So the equation Governing the potentiometric error detector is written as epsilon s is equal to ke into theta s minus theta c s, right? Next, coming to the amplifier, right? So amplifier has a gain of Ka as we stated. The output of the amplifier VAS is equal to the gain, that's Ka into epsilon s, right? So that completes the model for this amplifier unit, this equation. Okay. Next, what we have is the servo motor unit. So now here we are going to apply the knowledge that we have gained already, that is the model of the DC servo motor in the armature control mode has already been derived, right? If you have to derive it from scratch, maybe from the basics, you would have to repeat the same thing over here. So armature control, DC servo motor, consider all assumptions, etc., etc., write down the equations, and then finally arrive at the model, that is the output to the input transfer function. So here we are assuming that we know that the model of the model, meaning the transfer function model of the DC servo motor is actually known, but making appropriate changes, whatever is required, will be done. So here now, the DC servo motor, if you recollect, we had stated that the output of the DC servo motor is what? It is the angular position, and for that matter, it is the angular position of the motor shaft, right? So that is theta m. What is the input to the armature control DC servo motor? It is the voltage supplied to the armature. So VA is the input, right? So theta ms by VAS is going to give us the transfer function, right? Now transfer function we've already derived earlier, and if you would, I mean, you would basically recollect that it looked somewhat like this. I'll just, okay, I'll not switch slides. You would recollect that it looked like this, that is Ki by S into something over here, whatever is written over here, this was the model. The only difference is that now over here, the motor is directly coupled to the load. So now earlier what we had done is we had taken only the servo motor and we had derived its model. But here in this particular application, we have the information that the motor is coupled, the output of the motor, or rather the shaft of the motor is coupled to the load. So here the only modification that we have to make in the model that is already derived is that instead of the moment of inertia and viscous friction coefficient of the motor only, here we have to take the equivalent moment of inertia and equivalent viscous friction coefficient of the motor and load combined, right? So then the I mean those J and F can be put in the otherwise, I mean, intact model of the DC servo motor, and we can use the same model, right? So that is what has been done. So first of all, the equivalent moment of inertia reflected on the motor side is J, that's the notation that's being used, will be equal to Jm, which is the motor moment of inertia, plus gear train was taken, ratio was taken as N, so N square JL, this one, also written as Jm plus N1 by N2 whole square JL, where N1 by N2 is the gear ratio. So this would be the equivalent moment of inertia and denoted by J. Similarly, for the viscous friction coefficient, the equivalent viscous friction coefficient is F, and that is equal to Fm, that is the motor viscous friction coefficient, plus M squared Fl, right? If something is negligible, we'll, I mean, put that in at a later stage, no problem. So basically, these are the moment of inertia and the viscous friction coefficient of the overall motor plus load combined, right? So here now the transfer function becomes theta ms by Vs is equal to Ki by S into Js plus F. So where J is the equivalent J, F is the equivalent F, whole into Ra plus Sla plus Kb Kis. So the rest of the things you would recognize is the same as what we had derived, only the equivalent J and F have been considered. So here now from this, I mean, model, taking out or taking common Ra and F, what we have is we can express it in the time constant form like this, right? So 1 plus S tau n whole into 1 plus S tau a, etc. The rest of the things remain as it is. I'm not reading out all this, you can see that, right? Where now tau m, if we use that notation tau m, tau m is given by j by f. So we've taken out f common, and then that means that here you have j by f into s, and that j by f has been replaced by tau m. So you can understand, it's obvious. So tau m is equal to j by f, and tau a is equal to LA by RA. That is also, I mean, obvious. But here, if LA is negligible, naturally tau A is also going to be negligible. So if now tau A is negligible, we can, I mean, sort of put that this, I mean, tau A is approximately equal to, almost equal to 0, which makes us, I mean, forget about this term, right? So 1 plus S tau A will be just 1, right? So that this particular model is simplified to a second order model. Why second order? Here you will have Ki in the numerator. In the denominator, you will be having RAFS into 1 plus S tau m, right? So there is a second order term and a first order term, plus KB KIS, right? Because this is absent. That is what we will be showing next. So my transfer function for the DC servomotor unit, that is this unit over here, overall considering the load as well, is going to be given by theta m s by VAS is equal to this, right, where tau A has been neglected. Okay, if you are unable to understand anything, please let me know. I hope I can convey what I mean. So now if I just put, instead of tau m, you can just again put back j by f, just to uh, show what is happening. So putting in j by f over here instead of tau m. So just give me a moment. I will have to mute myself. Okay, can you see the slide and hear me? Just confirming because I had to mute myself. Can you hear me?
Yes, ma'am.
Right. So coming back, this tau m is equal to j by f, right? So basically, I mean, just putting that over there, and what we'll do is we'll collect terms, I mean, similar order terms. So basically, the second order term happens to be what you have, this RAF into S square into j by f. So that is the second order term. And then collecting first order term. So first order you have RA into F into S. So that's this one, plus KBKIS. So basically the overall model, that is transfer function model, becomes this. That is what you can see over here. So now in this model, dividing the numerator and denominator by this term, right? So this is what you get. You can see that written over here in the next step. Explicitly it's written. And then now, if you look at this, in the numerator you have Ki by RAF plus KB Ki. All of those are constants. Okay, so I mean, they will have to be considered the proper units and values, but it's a constant. The numerator, overall numerator over here, this whole thing, right? Similarly, here RAJ by RAF plus KBKI again is a constant. And the last one is of course unity. So basically we are rewriting this overall model in this form. It's, we are replacing the numerator by Km, K suffix small m, and in the denominator we have S common, tau m prime S plus 1, right? So basically the overall model has been reduced to a very simplified model, which is given by Km by S into tau m prime S plus 1, where Km is the motor gain constant. It's the name given to Km and is equal to the same thing that you have over here in the numerator, Ki by RAF plus Kb Ki. So the whole thing in the numerator has been replaced by K suffix small m. Similarly, the denominator, in the denominator, this is of course equal to 1, so that is there. Tau m prime will again be giving you the entire term that is multiplied with s square over there. So basically that is known as the motor time constant, and it is equal to Raj by Raf plus Kdki, whatever you have over here as the coefficient. So that enables us to simplify our model to a very, very simple model, which is this one. So this actually is the entire DC servo motor model when considering the armature control mode. Whatever is used over here, the entire this portion of the system has been modeled as this Km by time prime s square plus s, or whatever you see over there, right? So now from there, what we will try to do is we will try to first of all, consider or rather draw the block diagram, and also we will try to, try to consider the missing links. Links means if I just, come to the previous slide. Over here, we've got the model of this potentiometric error detector. We've got the model of this amplifier. We have also got the model for this servo motor unit, right? So what is left? We have got, as far as the servo motor is concerned, we've got it in terms of theta m by Va. So theta m is the output of the output angular position of the motor, right? Now, of course, in this overall remote position control system, we have something which is known as theta L, and theta L bears a ratio, depending on the gear ratio to theta m. So theta L and theta m are not the same. There is a gear ratio conversion has to be made. So that is one thing that we have to keep in mind. So appropriate conversion from theta m to theta L has to be made. Also, the feedback has not been considered so far, in the sense that if we draw the block diagram, we will be considering the feedback, which we see is basically theta L, which is being fed back as theta C. So theta C and theta L are the same thing. But till now we've got all the expressions, and as far as our expressions go, we've got the model, the last model, this one, this is servo motor model in terms of theta m. We have to make a conversion from theta m to theta L, then we can complete the loop. So that is what I meant, right? So basically, what we are going to do next is we are going to find out theta L by Va. So we have got theta m by Va. Now, in order to find out theta L by Va, what we have to do is we have done a very simple thing over here, theta m by Va into theta L by theta m. So what has been done is in the numerator and denominator, theta m has been considered extra, thus enabling us to break up this overall theta L by Va into two portions. What are the two portions? One is theta ms by Vas, which is actually the model of the DC servo motor, which we already have derived. Theta m by Va we've done on the previous slide. Also, the second portion, which is theta L by theta m, which is a simple gear ratio. So the gear ratio is basically N1 by N2, and that is equal to theta L by theta m. That is the conversion that has to be made. So in effect, theta L by Va will be equal to this transfer function multiplied by N1 by N2, right? So now from there, if we want to find out the, or rather before finding out that, let us try to draw the block diagram first, and then I'll come back to the open loop transfer function. So in the block diagram now, we find that the reference input is theta r, which was there for the the system that we considered, and not switching slides, you would recollect the schematic diagram that we had drawn. So theta r was the reference input. Also, this is the potentiometric error detector, this and the Ke taken together. So this overall block over here is the potentiometric error detector, which takes into consideration theta r minus theta c into Ke will give you the epsilon s. That was the model that we had derived, and it's remaining the same over here. So theta c is actually coming from theta L, and theta c is equal to theta L. So this directly, the output is theta L, and that is being fed back directly, right, via the negative feedback. So that completes the this potentiometric error detector, this portion, right? Next, we have the amplifier. So amplifier we know is the model was VA is equal to K into epsilon. So this block is going to complete the model. Next, we have theta m by VA, which is actually the DC servo motor the armature controlled mode. That model that we have just derived is given over here. The simplified model, I mean. You could have put the overall model, third order model also could have put. It's going to be a bit complicated, but nevertheless, you can put over here if your armature inductance has to be considered, meaning it's not negligible. Then you put the overall model over here. But for this analysis, we are going to go to the we are going to put the simplified model only, that would be sufficient. Next, we have theta m. So, in order to convert from theta from theta n to theta l, we would have to multiply by the gear ratio, which is n1 by n2. So, overall, this is what we have in the forward path, and then the unity feedback path. As I mentioned once earlier, I'll restate that if there was a gearing arrangement between this feedback which is being applied and the load angular position, then that gear ratio would have had to be considered in the feedback path. Here, the gear ratio is equal to 1 because there is no gear actually. So the coupling is direct, right? So now coming to the open loop transfer function. So open loop transfer function means from where to where? You have theta L on this side, and you have the on the input side meaning the input of the forward path is this error signal, right? So basically this from starting from ES up to theta LS, you can consider as the forward path overall. So
Ma'am,
yes.
I have a question, ma'am. That gear
Hmm.
train ratio, ma'am,
Yeah.
it in that gear train ratio, does it include only the number of teeth in a gear?
Sorry.
Ma'am, in that gear train ratio,
Uh-huh.
N1 by N2, uh, uh, is
The
there? I
overall
mean,
ratio,
the
whatever is the gear ratio we are
number
considering
of
over
teeth.
here. We are not going to, yes, we are not going to go into the details of, how you consider the gear ratio. The standard procedure will be adopted, right? So the ratio of conversion, the conversion factor is what we are considering over here. Okay.
Okay,
So,
ma'am.
huh. So the forward path will be considered. When we want the open loop transfer function, the forward path that is the error signal to the output signal is what we would be considering. So theta ls by es is the forward path transfer function. So you can see that it's written as, you can see ke into k into km into s km by s tau m s tau m prime s plus 1 into n1 by n2. So this entire thing is what constitutes the forward path transfer function, and it is denoted by gs, right? So that is the forward path transfer function. The feedback path, of course, has a unity gain, as you can see, it's unity. So this is the overall block diagram. And also here, we have seen that the forward path transfer function is also separately mentioned, right? So now coming back to what objective does this system have to meet? This system actually is a remote position control system, and we have stated that if we put in a signal at the input side, that is the reference signal is mentioned or given, provided to the system, the output or the load, basically load should be following the input signal, right? So tracking the input signal is the term we use, and that is the objective that has to be met by the system. So in order that that objective is met, what should be the, does it boil down to as far as control system is concerned? It means that in the steady state, the error between the output signal and the input signal should be equal to 0, or at least as small as possible. So the steady state error of this particular system should be as small as possible, so that in the steady state, at least your output shaft position is going to follow the reference or command shaft position, right? So now we try to find out what happens, what is the steady state error to this steady state error of the system if a particular input, say for example over here, we are going to consider only a step input, if a step input is applied as the command signal, meaning theta rs is equal to, say, it has an amplitude of capital theta. So this notation you find over here is a capital theta, so that excuse me, when you take the Laplace transform, theta rs is equal to capital theta by s. So that is the step input command that is being applied to this system. So now what we would want to see is whether the system performs the objective for which it has been designed. So in order to do that, what we have to do is we have to consider the steady state error for this system. So you would recollect that if you want to find the steady state error, that is the notation used is given over here, not a good notation, but nevertheless that is denoting the steady state error for this particular system. Steady state error in theta, that's why theta suffix ss is what we have denoted it by. But anyway, that is going to be equal to limit of es as s tends to 0, right? So where es is the error signal, this one. Okay. So now for that, in order to evaluate this, what we would have to do is we would have to find out es. Now you would recollect that the error transfer function, meaning es by theta r, would be what? It would be 1 by 1 plus gs, and hence basically you would be getting es as being equal to gs by es is equal to rs by 1 plus gs. I hope I've been able to convey that properly. I'll repeat because in the middle I sort of tried to repeat. So this is GS. GS is the open loop transfer function. This whole thing is GS, and you have 1 as the feedback path transfer, transfer function or feedback path gain. So ES will be equal to what? ES is equal to the input by 1 plus GS, right? Because ES by theta rs would have been equal to 1 by 1 plus GS, right? So from there, now if you multiply theta rs to both sides, you will get ES, which is equal to theta rs by 1 plus GS. So now that is the basis of what we've done over here. So limit of SES as s tends to 0 would be equal to limit of s into rs, which rs means theta rs, theta rs, which is theta by s, right? So s into the input signal is what we find over there by 1 plus gs. So this gs has been put directly from there. So now evaluating this, you find s and s cancel out, and now if you evaluate that, can you verify whether you get the value properly? Can you just verify and tell me if you evaluate this limit, what you get?
Zero, ma'am.
Yes. So yes, that's correct. So basically, because you have this s in the denominator, you have to multiply over here and there and etc. So when you take the limit, that is going to be equal to 0. So that implies that the steady state error is equal to 0, which implies that if I put in a theta r over here, ultimately there will be no, ultimately means in the steady state, there will be no, difference between my output signal and the input signal. Means the steady state error will be equal to 0. That would imply that my load shaft would be closely following the input shaft. Whatever command is given to the input shaft, basically the load shaft will follow that, right? Now, the question may arise that basically over here, if okay, so if there is some change in the command signal, naturally now again there will be transients, but ultimately again the steady state, since the error is going to be 0 in the steady state, theta L will finally converge to again the new value that you have put over there. So whatever be the input position that is given, basically will be followed at the output side, right? So this is used in, as remote position control, in remote position control system, meaning that, as I told you earlier, person sitting in the control room will be giving the command, and somewhere else at a remote location, wherever it is, the radar would have to, the shaft of the radar will be actually radar or dish, whatever is being, the dish of the system, that is, basically would have to have an angular orientation which is going to closely follow the command that is being given from a remote location as well. So basically, this is how the system achieves the task of following a given target. Here, of course, the output will be depending on whatever input command you have given. Manually, that can be given. What I've discussed so far is that you are giving a manual command. Also, it may be that somehow automatically this command is being given, in which case automatically the output will be following the input, right? Next, what we come to is till so far we have not considered the effect of any disturbance or load torque on the system. But now what we are going to do is we are going to, okay, before showing you this particular slide, let me just go back one of the slides. Okay, let us see this photograph over here itself. So now if, say, for example, the dish is pointing in a particular direction and there is a storm which is going on, what will happen? Automatically, the shaft over here for this dish antenna is going to be displaced from the desired position, right? So the effect of such disturbing torque is what we are going to consider next, right? Now, for that, what we are going to do is we would have to, since the disturbance comes in the form of a disturbance torque actually, and in the block diagram that we had derived and in the entire model, we had not actually explicitly dealt with the motor torque. The torque produced by the motor implicitly, of course, is there was a torque which was produced, but in the model we did not write any expression. You would recollect when we were writing the expressions for the DC servo motor only earlier in the previous day when we were deriving the model, there we had expressions for torque. Now here, since we have considered the entire model of the DC servo motor at one go, we have not mentioned about torque. But in order to consider the effect of disturbance torque, what we would have to do is we would have to again, see what the torque produced by the motor is, and then see the effect of the opposing torque, meaning the disturbance torque, which is going to be externally applied by some factor. As I told you, a strong wind may be the factor which is disturbing it. So now what is being done as far as the model is concerned, this particular block, that is the motor block, this is servo motor block transfer function, is being broken up into two parts. How is it broken up into two parts? You see this dotted blue block is the entire, light blue colored block that you see over there. So this entire block has been broken up into two portions. One portion is what? There is another constant which has been introduced, K suffix capital M, which is known as the motor torque constant, and it is converting from the applied armature voltage to the motor torque, that is Tm, and then the rest of the transfer function, rest meaning this entire thing is being broken up. So what I'm saying is that after taking out Km, whatever is left will be here the conversion factor between the torque to the angular position. So overall, for this dotted blue block, you find the input to the block is Va and the output is theta m. So it is the same as that you see in the top diagram over here, this light blue block. But internally, it is being broken up such that we are able to see what is happening to the motor torque. So now coming to what's written over here. Okay, so the breaking up has been shown over here. I hope you can see the cursor again. So Km by S tau m prime S plus 1, this has been written as Km by S into, now tau m prime has been written in terms of the equivalent J and the equivalent F. Here the notation is given with EQ, equivalent is what I mean, right? So basically tau m prime is J equivalent by F equivalent, that has been written over here into S plus 1. So this is broken up. Now what is done is you multiply numerator and denominator by the F equivalent to get this, that is K into F equivalent by J equivalent S square plus you have over here F equivalent into S. So basically this can be written as this. Now the numerator is replaced by K suffix capital N, which happens to be the motor torque constant and denoted by K suffix capital M, and is equal to whatever is there in the numerator, meaning K small m into F equivalent, right? And now in the denominator, you have left J equivalent S square plus F equivalent S. So now if I write this as, I mean, dividing it into two parts separately and then cascading them together, you have Km, that is K suffix capital M, into this, that is 1 by J equivalent S square plus F equivalent S. Why this breaking up has been shown is that we want to actually break it up into two separate blocks, one which is going to be converting from the voltage to the torque, and then from the torque, the other one from the torque to the angular position. So basically this is done. So the block has been broken up. So now once the torque is visible over here, we can try to actually see what the, okay, the next slide actually is devoted to the units, and it has been shown that basically the units of, if you are interested, the unit of K capital M is Newton meter per volt, and K small m was equal to radian per volt second. So basically, I mean, that matching has been shown over here. I'm not going to go into the details. In some of my previous year students had confusion regarding the units. That's why it's shown over there. Obviously, in the PDF that you have received, that is also shown. And in case you have any sort of confusion, you can ask in the class, next class maybe, so that we can discuss if necessary. But I don't think it would be necessary because it's explained, it's written in a sort of detailed manner over there in that slide. So coming to the block diagram, we have the Km, which is converting from VA to Tn, and then we have this block which is converting from the Tn to theta n. So if there is a disturbance torque which is, I mean, disturbing the angular orientation, that torque will be coming at some point over here and basically opposing the torque that is being produced by the motor. So the overall torque which is going to be converted to the angular orientation of the motor is going to be a, I mean, an algebraic summation of the two torques. One the motor torque, the other is the disturbance torque. So the disturbance torque has been shown by a negative sign over here, obvious, I mean, for obvious reasons. So now coming back to the model, we had the potentiometric error detector model over here. It's the same as what we had earlier. Epsilon s is equal to Ke into theta rs minus theta cs. And we have the your amplifier model as VAS is equal to Ka into epsilon s, this portion, right? Now, instead of epsilon s, from here we put in Ke into theta rs minus theta cs. So VAS is equal to this Ke into theta rs minus theta cs. Okay. So next we come to the developed torque. So torque developed is equal to Km into VA, right? K capital N VA. So torque developed is equal to K capital M into VA. Now VA has already been written as Ka into theta rs and theta cs. That is substituted over here. So that Tm is equal to this entire thing. Now in this entire thing, you find that Km into K into Ke, all these are separately constants such that the product is a constant. So that is replaced by another constant which is denoted as capital K. So K is equal to Km into K into Ke. If you now take the units, the unit of K will be Newton meter per radian. And where Km is the motor torque constant in Newton meter per volt. So this also you can verify, you can see, okay, Km is Newton meter per volt. Ka is what? It is volt per volt, right? And Ke is how much? It is, you find your output is in volts, input is in angular angle. So basically it's volt per radian. So I mean effectively if you multiply the three together, you will get Newton meter per radian as the unit of K. Okay. So Tm is equal to K into theta s minus theta cs. Okay. So next what we do is for simplicity in this analysis, what we sort of do is we make a simplifying assumption. This is not in general. In general, if you do have a gear ratio which is non-unity, you have to consider that. But just for simplicity of analysis over here particularly, this N1 by N2 has been considered as 1, in which case theta M and theta C are also the same. So we had already theta L is equal to theta C, and that is also equal to theta M, provided, I mean, in the specific case where we consider N1 by N2 is equal to 1. Just to simplify matters a bit, we know that, okay, if this is non-unity, you will have to take the appropriate ratio. So theta C by theta M will be equal to N1 by N2 if it is non-unity. But here, for this analysis, we are assuming no gear reduction between the output shaft and the motor shaft, that is between this and that. In fact, two things have been mentioned. So between the output shaft and the load shaft to the motor shaft, both are taken as 1, right? So earlier we had already taken this ratio between the load shaft and the output shaft as 1. Here we are further simplifying matters. So it's not simplifying, actually we are making a simplifying assumption which is going to simplify things for us a bit, knowing that if there is a non-unity gear train, you have to consider that this ratio has to be considered. So now when that is, I mean, what we have assumed, we now try to write down the rest of the equations and hence arrive at the model when a disturbing torque is present, right? So when a load or disturbing torque is acting on the motor, we have actually the motor torque is, I mean, it has to sort of balance both the load torque as well as the torque which is being, I mean, the rest of the torque, or rather, if we go about it in a different way, this torque that we get as, I mean, the actual motor torque after considering the effect of the disturbance torque, if we have to take that, this signal, that is going to be a difference between the torque produced after making this conversion minus the disturbance torque. Algebraic summation is what we have to do. So here we have Tm, that is the torque produced by the motor, is equal to the sum of the opposing torques. And now instead of Tm, you would recollect that on the previous slide we had got this, that is K into theta r minus theta c was equal to Tm, that has been substituted. That is equal to sum of the opposing torques. So what are the opposing torques? One is that if we, I mean, sort of from this theta m, if we want to see what the torque over here was, basically this torque, this quantity is also going to be a torque, isn't it? Effective torque, you can say, when we take the difference between these two. So this torque will actually be multiplied by this to get theta m, so that from theta m and this, if we want to get back the torque that was, I mean, in the input to this block, that torque will be given by J equivalent S square theta cs plus F equivalent into S theta s, isn't it? So basically what we have done is theta ms by this torque is equal to 1 by J equivalent S square plus F equivalent S. Now from there, this torque is equal to this portion only, the first and the second terms on the right hand side. Plus we have the load torque, right? So basically, or the disturbance torque as we call it. So now this is the overall expression that we get, the torque balance equation, right? So from here now, what is being done is only similar terms are going to be collected, so that theta r comes to the left, is there on the left side. TL also is taken to the left side, whereas theta c into K is taken on the right side. So this is what we get. Now, as far as this particular system is concerned, this system means this overall system is concerned, we have one output, that is the output of the load shaft, right? So output of the load shaft, or the output shaft, whatever you call it, is theta c, that is the output of this overall remote position control system. What are the inputs to this system? There are two inputs to this system. One is the reference or command input. The other is the disturbance torque. So as far as the system is concerned, system does not know which is your desirable input, which is the disturbing input, right? So it has two inputs. And so, I mean, when we want to get the transfer function for this particular system, or rather, let me say the model of this overall system in the transfer function form, we would have to consider both the transfer functions with respect, the transfer functions with respect to both the inputs. So there will be one transfer function in terms of the output to the reference signal. There will be another transfer function in terms of the output to the other input, which is the disturbance torque. So that is what we are going to see over here. So basically, this from this expression we've got this. So or rather dividing the right hand side and left hand side by this coefficient of theta cs, we are going to get the next slide. This from this is what we get. So theta cs is equal to now k into theta rs by j equivalent s square plus f equivalent s plus k minus TL by j equivalent s square plus f equivalent s plus k, right? So here we note a thing, as I have already stated, that there are two inputs. One is this, that is the reference input. The other is the disturbance input. But I mean, the output is going to be dependent on both of these. So from here now, we'll do one or two things. The first of which is that we are going to consider that both the desirable input, that is the reference input, and the disturbance torque, both of them are steps with respective magnitudes. So we consider that the magnitude of the reference input is capital theta, and the magnitude of the load or disturbance torque is TL. So this TL is apparently, I mean, similar in notation to the TLS that we had, but here the italics has not been used. So this is a constant. TL over here is the constant amplitude of the step that is being applied as the disturbance signal, whereas this TLS is it's not a constant value, right? So TLS is basically the input signal, but the value of which is yet to be determined. So here specifying that TLS is equal to, it is a step having an amplitude of TL. We have TLS is equal to capital T suffix capital L by S. Here you note again that here the italics has not been done for the magnitude where we are representing. Of course, it would have been better if I could have used a different notation, but unfortunately that is not being done. Whereas anyway, so you can understand. So TLS is equal to this constant magnitude TL by S, because we are applying a step, and theta rs is equal to constant, that is capital theta by S, right? So applying these two step inputs with respective magnitudes, we have the output as here, instead in this expression, instead of theta rs, simply you have put in capital theta by S, and instead of TLS you have simply put in TL by S, right? So this is the output signal. So now coming back to what objective we were looking for, that is, we wanted the remote position control system to be acting such that it would be tracking the input signal, the command signal, right? So let us see whether that has been achieved. So for that, again, what we try to do is we find the steady state output over here. Instead of steady state error, what we are trying to do over here is we are trying to find out the steady state output, and then we'll see whether the steady state output, how far it matches the input, right? So theta c in the steady state is what we go for over here. This is not the error that we are showing. This is the output only. If you want the error, you have to subtract the output from the input signal to get the error. So theta c in the steady state is going to be given by, again, applying your final value theorem, limit of s theta s as s tends to 0. So that is what we have to do. Theta cs we have over here. So putting the entire theta cs over here, and then taking the limit as s tends to 0 for s into theta cs. If you evaluate that expression, you see s and s cancel out. In the numerator, you have k theta, and capital theta, I mean, denominator, you have k. So basically, this first part of the expression is going to boil down to a capital theta only. The second one, you see again, this s cancels out with this common s. and again this S is 0, this S is 0. So you are left with TL by K, so with a negative sign. So ultimately, the steady state output is going to be capital theta minus TL by K. Okay, so that is my steady state output. So now if we want to find out how far the objective is met, objective meaning the tracking objective, objective that the output is going to be following the input in the steady state, how far that is met. So if you have say TL, that is the disturbance torque, is equal to 0, in that case you have the output as capital theta. The input step that was applied had an amplitude of capital theta. So in case your disturbance torque is equal to 0, your output will be following the input. So the objective is met, right? However, if there is a disturbance torque now, the output is going to be theta minus TL by K. So that if you subtract that from the input step that was applied, that is capital theta, you will be left with the TL by K, which is going to be the amount of the steady state error. So you will, if there is a disturbance torque, you will actually be getting a steady state error equivalent to TL by K, right? So the steady state error is proportional to the disturbance torque and inversely proportional to the gain K of the system, right? So now if somebody tells, okay, now I have a disturbance torque, I want to reduce it. Please design my system. Tell me how to design the system so that I can reduce the steady state error as much as possible. So that what can be done as far as design is concerned. So, okay, theta was theta, and if you take the difference with the input that is applied, this is not going to be there. The steady state error is TL by K, right? Now, TL is the amplitude or magnitude of the input signal. So, input signal means the disturbance signal, I mean. So, that you cannot do anything about. So, the only way that you can reduce the error in the steady state is that you can try to reduce this term. And by, for reducing this term, you cannot do anything to TL. So what can you do? The only thing that you can do is you can try to increase your gain K as much as permissible, right? So if you increase K, what will happen? TL by K will be small, and if you increase it further, TL by K will be smaller, so that even if you have a disturbance torque, by increasing the gain K, you will be able to reduce the steady state error, right? So having said that, there is a rider to that. Rider means that, I should, express something that is a word of caution over here, which is going to be like this. That is, okay, for reducing the steady state error, the gain K has to be increased as much as permissible, meaning if I were given a free hand, maybe I would have the tendency of making K infinitely large so that TL by K will be very small, right? However, the word of caution is that the steady state performance is not the only thing that is of interest as far as a particular system's performance is concerned. So if you increase the gain K, there are a lot of other problems that will crop up in the system. One of which, the most important of which, is that the system response will become oscillatory and to the point that it may become unstable. In fact, you would have done, root locus or other stability analysis criteria, you can verify that the stability of the system as far as the relative stability is concerned, by increasing the gain K, the relative stability becomes smaller, meaning the stability decreases. So that it is not possible to increase gain K as much as you want. So basically what has to be done is what we call a trade-off, trade, TRADEOFF, trade-off, meaning that, okay, in order to reduce the effect of the disturbance torque, I'll try to increase the gain K. But again, I will not be increasing the gain K, sort of infinitely, because I have to keep in mind the effect that it is going to have on the transient performance and the stability as well, right? So basically, K can be only limitedly, or in a constrained fashion, you can increase gain K to obtain a smaller steady state error. But as I told you, you have to keep in mind that that is also going to have effect on the stability. And if you are doing the design from this point of view, you would also, simultaneously have to do the have to do the stability analysis as well to see whether your stability requirements are also being kept intact while decreasing the steady state error, right? Steady state error when the disturbance plot is present. So basically, that is that is all as far as today's this remote position control system is concerned. So if you have queries, I've already taken up a bit more of the time. It's already 43. If you do have queries, you can ask either today or later on.